these two alveoli are interconnected. Okay. Now the question it is asking, two alveoli of different sizes, two alveoli of different sizes are connected to a common airway, right? If the surface tension is same in both the alveoli, the pressure produced by the surface tension will be higher in which alveolus and in which direction air will flow between the two alveoli. Okay. So the thing is, this situation is unstable. Okay. This situation is unstable. Okay. So it will not remain like this. It will not remain like this. Either one will blow into two or two will blow into one, and finally there will be a single alveoli. Right? And finally there will be a single alveoli. Okay. Now the question is, what will happen? What will happen if the surface tension is same? Okay. What will happen if the surface tension is same and pressure is different between the two alveoli? What will happen? Whether one will blow into two or two will blow into one. This is the question. Okay. So to answer this question, and this question is a problem solving type of question, you may expect in coming exams as well in your practical, right? So to address this problem, we need a formula. Okay, we need a formula, a law, and the law is called, anyone? Laplace law. Okay, so there is application of Laplace law in almost all hollow viscous, like the heart, the urinary bladder, the alveoli, and also the blood vessels. We can apply Laplace law. Okay, so আমাদের যদি Laplace law জানা থাকে তাহলে we can easily solve কি one will blow into two or two will blow into one, and ultimately there will be a large single alveoli. ঠিক আছে? So what is Laplace law? I'm coming to it. What is Laplace law? But similar kind of another problem I have in cardiovascular system, because this is two alveoli, these are from respiratory system, right? This problem is from respiratory system, from your respiratory system. But yes, it is a problem. Two alveoli are connected of different sizes and they are interconnected, and this system is totally unstable. Okay, this system is totally unstable. Either one will blow into two or two will blow into one, and there will be formation of a single alveoli. This problem is from a respiratory system. In cardiovascular system, we have another problem. Okay, so another problem from cardiovascular system. Okay, so let me come to the systemic circulation, the beginning of systemic circulation and the ending of systemic circulation. Your systemic circulation begins at, from which blood vessel? Systemic circulation begins at which blood vessel? Aorta. Aorta, right? Okay, left ventricle is pumping through aorta. Aorta theke arteries, small arteries, arterioles. Arterioles break into capillaries. From capillaries, venules, veins, vena cava, and again into right atrium. Okay, so this is your systemic circulation. So your systemic circulation begins from the left ventricle and aorta, and your systemic circulation is ending through vena cava into right atrium. Okay. Now what do you expect? Pressure will gradually increase or decrease? What? Decrease. Okay. That is why blood is flowing. Okay. From aorta, from LV to aorta, to arteries, to arterioles, to capillaries, to venules, vein, vena cava, and ultimately right atrium. Pressure is falling, pressure is falling. That is why blood is flowing from aorta to right atrium. Right? Okay. So what is the pressure, mean pressure in aorta? What is mean pressure in aorta? Mean pressure in aorta. Aorta mein pressure kya hai? 120/80. What is mean pressure? Mean pressure is diastolic blood pressure plus 1/3 of pulse pressure. If you calculate it, it will come to 93.3 millimeter of mercury. Okay. So for rough calculations, say for example, the mean pressure in aorta is 95. Okay, 95. Then arteries 90. Okay, mean pressure is gradually falling. That is why blood is flowing from aorta to arteries, right? Then more small arteries 60 maybe. Okay, arterioles far less. Say for example 20, not 20, say 50. Okay, then capillaries 25. Okay, then venules say 20. ठीक है, venules and vena cava 20, then vena cava 10, then right atrium far less 5. Okay, this is why this is how blood pressure is falling. Okay, and this is why due to this pressure difference only, okay, due to this pressure difference, aorta to arteries pressure difference is 5 millimeter of mercury, so blood will flow from here to here. Again there is a pressure difference from large arteries to small arteries, pressure difference of 30, so blood will flow, right? So gradually blood will come to right atrium. LV is pumping from LV, pressure is 120, right? So from LV to right atrium, this total circulation is systemic circulation, and the cause of blood flow is pressure difference, simply pressure difference. Okay, now I will put you in a trap. Okay, and that trap is, forget everything, just look at the capillaries and look at the vena cava. Okay, what is capillary? Capillary is the single layer of endothelial cells over a basement membrane. Ar kichui nahi, right? So capillary, if we check, there is a basement membrane and a single layer of endothelium. Okay, this is capillary, very weak. Its wall is very weak. And in comparison to vena cava, it has typical tunica intima, tunica media, tunica adventitia, all the elastic tissues. This is vena cava. Okay, this is the vena caval wall. Lots of fibrous tissue. Sorry, lots of elastic tissues. Okay, and also the endothelium as well. Itna sa thick, right? This is vena cava. Okay. So you are putting a pressure of 10 millimeter of mercury inside vena cava and a 25 millimeter of mercury in capillary. And capillary is supposed to withstand this much pressure. Getting my question? Okay. Wall thickness capillary में बहुत कम है, right? Because the capillary is a single layer of endothelium upon a basement membrane. ঠিক আছে, একটা thin basement membrane এর উপর অনেকগুলো সেল রয়েছে. This is capillary wall. It can break easily, right? And inside the vena cava, it has typical blood vessel layer, tunica intima, media, adventitia, lots of elastic tissues, fibrous tissues, collagen, right? It can withstand many fold of pressure, it seems, right? So vena cava আমি 10 millimeter of mercury pressure দিচ্ছি and capillary তে 25 millimeter of mercury pressure দিচ্ছি. Is this not an injustice? कैपिलरी एक वीक बच्चा है और उसको मैं 25 mm Hg प्रेशर दे रहा हूं, और वेना केवा इज क्वाइट स्ट्रॉन्ग, उसको मैं सिर्फ 10 mm Hg प्रेशर दे रहा हूं. ठीक है, और ये प्रेशर डिफरेंस रहना भी पड़ेगा because this pressure difference due to this pressure difference blood will flow from capillary to vena cava. This pressure difference is required also. Okay, but how capillary is supposed to withstand this much of pressure? Okay, clear question? Okay, abar capillary te pressure beshi rakhte hi hobe, otherwise blood will not flow from capillary to vena cava. Okay, otherwise the direction will reverse. Okay, jodi pressure ekhane 25 hoy, ekhane 10 hoy, তাহলে ব্লাড উল্টো দিকে ফ্লো হবে। ওকে, I need blood flow from capillary to venules from to vena cava, right, in this direction, and this is why pressure need to be more inside. Pressure means distending pressure, the pressure which is acting longitudinally towards the wall of the blood vessel, right? This pressure, distending pressure. So the distending pressure which is trying to tear the capillary wall, and the distending pressure which is trying to tear the vena caval wall is different. Okay, capillary খুব weak, okay, capillary খুব weak, ওখানে 25 mm Hg প্রেসার দেওয়া আছে, আর vena cava যেটা খুব স্ট্রং ওখানে মাত্র 10 mm Hg প্রেসার দেওয়া আছে। Okay, so how is it possible? This is another question, another problem solving question. Okay, okay, now both this problem, this one and this one, we can solve with Laplace law. Okay, both of this problem can be solved by Laplace law. So what is Laplace law? Always remember the statement of Laplace law. It is stated as the distending pressure in a distensible hollow organ including blood vessels. Okay, distending pressure in a distensible hollow organ is proportional to wall tension, and inversely proportional to the radius of the curvature. Okay, I repeat, distending pressure in a distensible hollow organ, distending pressure in a distensible hollow organ is proportional to wall tension and inversely proportional to radius of the curvature, right? Okay, so distending pressure is P. Okay, distending pressure is P. It is inversely proportional to the wall tension and inversely proportional to the radius of the curvature. Okay, so for an organ like a blood vessel, we can assume that T is equal to P into R. Clear? Okay. Okay. Now, P for vena cava is equal to T for vena cava. That means vena caval wall tension. Vena caval wall tension is P into vena caval pressure is 10 millimeter of mercury into R vena cava, right? And for capillary wall tension is equal to 25 into RC. Clear? So tension vena cava by tension capillary is equal to R vena cava by R capillary. এত দূর ক্লিয়ার কিনা? Yes? Yes. Put the values as well. 10 by 25. That means 2 by 5. Clear? Okay. Now the thing is, this R vena cava is of the capillary. Correct? This is why tension in vena cava is also much higher than tension of the capillary. Clear? Okay. Now, the thing is, even if the pressure inside vena cava is much lower than the pressure within the capillary, wall tension of vena cava is much higher than the capillary. Getting my point? So actually, it is not the distending pressure which is trying to rupture a balloon. Okay. If you blow a balloon, it is not the distending pressure which is acting from inside to outside, which is the cause of rupture of the balloon, right? The cause of rupture of the balloon is its wall tension. Clear? It is the wall tension, and all the internal organs, including the blood vessels, are designed in such a fashion that they are able to withstand wall tension and not the distending pressure. The more is the elastic tissue, the more will be the wall tension. Okay. So whoever, the Almighty, has created a human body, keeping in mind that the more is the requirement of wall tension, the more will be the elastic tissues, right? Simply take aorta, lots of elastic tissues. Why? Because aorta needs to deal with more wall tension. Okay. Forget distending pressure, because rupture of an organ, it doesn't depend on the distending pressure which is acting from inside to outside. Apparently it seems it is the distending pressure which is the cause of rupture of a blood vessel, right? Apparently it seems, but it is not the distending pressure, it is actually the wall tension which is responsible for rupture of an organ or rupture of a blood vessel. So capillary, which is devoid of any elastic tissue, capillary में कोई elastic tissue नहीं होता है, only cell. So it seems that with the 25 millimeter of mercury distending pressure, capillary will rupture easily. But if you think of wall tension is quite low in capillary wall. Okay. So God has given elastic tissues where wall tension is more, right? Like the vena cava, like the aorta, the arteries. Okay. So elastic tissues, presence of elastic tissues plus in aorta, plus in vena cava, okay, 0 in capillaries. Because in capillaries, wall tension is almost 0, insignificant. The more is the wall tension, the more will be elastic tissues. Okay. So it is not a matter of distending pressure, it is a matter of wall tension. Okay. Even if the pressure inside the capillary is quite high, the capillary is having lowest wall tension. That is why no elastic tissues required here. Okay. Apparently it seems that distending pressure is responsible for the rupture of an organ, but actually it is wall tension. Clear? Okay. Now how to solve this problem? Same by applying Laplace law. This one clear to everybody? Yes, answer is 1 to 2. Answer is 1 to 2, but you need to explain why air from alveoli 1 will blow into alveoli 2, and there will be formation of a larger alveoli, right? Okay, so wall tension here is the surface tension. Okay, in lung there is surface tension. Gradually respiratory system হয়ে গেছে হচ্ছে. Okay, শুরু হয়নি. Okay, so in subsequent classes we will talk about surface tension in lung and what are the problems and diseases associated with low surface tension. What are the substances which are responsible for maintaining surface tension in air-water interface in the alveoli that maintains the patency of the alveoli. Without surface tension and without surfactant are the material which are secreted from pneumocyte cell, particularly type 2 pneumocyte cells, and it contains few things like lecithin and some proteins. Okay. So we'll come to it gradually. It is not the right platform to discuss everything about surface tension and surfactant. So surfactant is a natural substance which is present in our lungs and that reduces surface tension. That is why our alveoli are patent and we are able to breathe in and breathe out. Otherwise, alveoli will be collapsed. Okay. So anyway, so the pressure inside is surface tension and it is same for both 1 and 2. It is telling. So from the Laplace law, we know that P is equal to T by R, right? So for alveoli 1, P1 is equal to T by R1 or T is equal to P1 R1, and for alveoli 2, it is P2 is equal to T by R2, so T is equal to P2 R2, right? Now both of these are same because surface tension is same, so P1 R1 is equal to P2 R2, right? And P1 by P2 is equal to R2 by R1, and you know R2 is higher than R1, right? So P1 is greater than P2. Clear? So inside P1 pressure is high, inside alveoli 1 pressure is high, and inside alveoli 2 pressure is less. And the simple rule is any fluid or air will flow from high pressure to low pressure. Clear? So 1 will blow into 2. Okay? Very simple. Now we'll talk about peripheral resistances. Peripheral resistance. You have two different types of circulation. One is your systemic circulation that we just talked about, which is starting from aorta and ending in the right atrium. It is your systemic circulation. Similarly, where is the beginning of your pulmonary circulation? Pulmonary artery, and it is ending at left atrium. Okay. Your pulmonary circulation is beginning at from right ventricle to pulmonary artery to lungs, okay, and from lungs through pulmonary veins, it is right atrium. Okay, clear? So two different circulation. One is systemic circulation, another is pulmonary circulation. And in our previous discussion, many times we have mentioned that the resistance in the systemic circulation is much higher than pulmonary circulation, right? And this is why your left ventricle is stronger, right, than your right ventricle, because your left ventricle is pumping blood into systemic circulation, which is a high resistance circuit, and your your right ventricle is pumping blood into pulmonary circulation, which is a low resistance circuit. Okay. Okay. Now we will actually calculate the resistance. How much is the resistance in the pulmonary circulation and how much is the resistance in the systemic circulation? Okay. Due to circulation and resistance er ki partho, right? Okay. So to calculate resistance, simply we will apply Ohm's law of hemodynamics. Okay. You have already read Ohm's law from your 10+2, but it is for electricity. It was for electricity, right? And the formula was V is equal to, correct. So V is a potential difference, but for hemodynamics it is pressure difference. For hemodynamics it is pressure difference. Okay, so it is pressure difference. I is flow of electricity, ampere, right? Flow of electricity I. So in our context, hemodynamics, it is blood flow. Okay. In hemodynamics, it is blood flow. We mark it with Q. And R is the resistance. Same. R is the resistance. Okay. Resistance is equal to pressure difference by blood flow. Okay. Resistance is equal to pressure difference by blood flow, right? So here is the details of pulmonary circulation. Here is the details of pulmonary circulation. Your pulmonary circulation begins at pulmonary artery and your pulmonary circulation ends at left atrium. Okay, left atrium. What is the pressure difference? Pressure यहाँ पर दिया हुआ है already. ठीक है? And pressure difference they have already calculated. Okay. So the pressure difference is 15 minus 8, that is 7 millimeter of mercury. 7 millimeter of mercury is the pressure difference. Okay. So resistance in the pulmonary circulation, let us calculate resistance in the pulmonary circulation. So del P, pressure difference is equal to 7 millimeter of mercury. What is Q? Blood flow. কত এর value? Normally. এই blood flow actually key. Yes, cardiac output. Very nice. Cardiac output. Okay. This flow is actually cardiac output, which is 5 liter per minute. Okay. For both the ventricle, whether it is left ventricle or right ventricle, your cardiac output is 5 liter per minute. Okay. But here we need to calculate liter per minute. We need to calculate it at ml per second. Right? ml per second. So if we consider a normal healthy human being, adult, cardiac output is 5 liter per minute for both right ventricle and left ventricle. Here it is right ventricle because it is pulmonary circulation, right? So right ventricle's cardiac output is 5 liter per minute. If you convert it into ml per second, if you calculate it, it will come to around 83 ml per second. Okay, 83 ml per second. Okay, almost 83 ml. 83 will be coming out. Okay, 5 liter per minute is equal to 83 ml per second. Okay, so this is the flow, 83. Now the resistance in the pulmonary circulation, RP, resistance in the pulmonary circulation is equal to 17 by 83. Okay, কত আসছে এটা? Anyone একটু ক্যালকুলেটরে যদি দেখো, 0.1 or something. 7 by 83. 0.084. Okay, 0.08. এতদূর লিখলাম. Okay, 0.08. And the unit is called PRU. 1 PRU. PRU means peripheral resistance unit. Peripheral resistance unit. Okay. So 0.08 PRU is the resistance in the pulmonary circulation. Clear? Now let us calculate the resistance in the systemic circulation. A resistance 0.08 PRU. A resistance against act korche your right ventricle. Okay, your right ventricle has to pump blood against this much resistance, 0.08 PRU. Okay, now we will calculate for left ventricle. Your left ventricle is working against how much of resistance? So your systemic circulation is being generated at aorta. Aorta থেকে শুরু হচ্ছে systemic circulation, and the pressure is 95 millimeter of Hg, right? And your systemic circulation is ending at right atrium. Okay, aorta, arteries, arterioles, capillaries, venules, vein, vena cava, then right atrium. Okay. Yes. Right atrium. Oh, resistance you have already calculated. Okay, very good. Okay, so let us calculate. So aorta 95 and right atrium 2. The net pressure difference is 93. Yes, sir. Okay. এটা কি হলো? Okay, so RS, resistance in the systemic circulation is 93 by 83. It will be 1.1. Right? 1.1 PRU. Okay. So simply you can see that peripheral resistance in pulmonary circulation is much lower than the resistance in the systemic circulation. Clear? So your left ventricle has to pump blood against 1.1 PRU and your right ventricle has to pump blood against 0.08 PRU. This is the basic concept you need to have. Okay. Now, you have known Laplace law and Ohm's law in hemodynamics, right? Ohm's law in hemodynamics. Now this resistance R, it has got another formula, and this is R is equal to 8 okay, 8 eta L by pi r to the power 4, where R is the radius of the curvature and L is the length and eta is viscosity. Okay, viscosity. Okay, and you may have many problem solving question by application of this formula as well. Okay, Poiseuille's law. Okay, it is called Poiseuille's law. So you may have some simple mathematical question or any explain why question by simply application of this, by changing radius or by changing viscosity. And mostly in our clinical setting, what matters is the viscosity. Okay, radius also matters because of sympathetic activation due to vasoconstriction, vasodilatation. Radius matters, and also matters with the viscosity. Okay, and what are the parameters in blood upon which viscosity depends? Okay, so viscosity depends, number one, on hematocrit. The more is your hematocrit, more will be the viscosity. Okay, more will be the viscosity. And secondly, second important thing upon which your viscosity depends, viscosity of blood depends, is protein. Okay, protein content like fibrinogen. Okay, if increases in blood, there will be increased viscosity. And two common diseases with high viscosity, where hematocrit increases. So when hematocrit high, when hematocrit is high or the protein content is high, what will happen? Viscosity will be high. And what will happen to the patient if the patient's viscosity is high? What will happen to the patient? Resistance is high. Simply, resistance is high. So blood flow is sluggish, right? Blood flow is sluggish. So there will be less tissue perfusion. Okay. So there will be less tissue perfusion or end organ hypoxia. So the patient will be complaining of fatigue. Okay. Patient will be complaining of fatigue. Anyway, so name two diseases where viscosity is high. I have already given clue, that is high hematocrit and high protein content. Okay. So high hematocrit is seen in polycythemia. Polycythemia, where your RBC count is high. Okay. Polycythemia. Again, polycythemia is of different type. One is relative polycythemia and another is absolute polycythemia. Relative polycythemia is when someone moves to high altitude, there is relative polycythemia, and also when someone is smoking for a chronic period, right? Then there will be polycythemia. It is relative polycythemia. But what is absolute polycythemia? Absolute polycythemia is also called polycythemia rubra vera. Okay, polycythemia rubra vera. It is a genetic mutation in the JAK-STAT protein. Okay, have you heard JAK-STAT? Okay, so it is a mutation in the JAK-STAT protein through which erythropoietin acts. Okay, erythropoietin is a hormone which is secreted from the fibroblast cells of kidney. Okay, erythropoietin, and in this JAK-STAT mutation, it is a gain of function mutation. Gain of function mutation means erythropoietin will act more than what it's supposed to be, right? So in this case, more and more RBCs will be produced and there will be viscosity, and the patient will be complaining of fatigue, fatigability, easy fatigability. right? Okay. So this is high viscosity due to increased hematocrit, and another thing is high viscosity due to protein. An example is, you don't know, it is multiple myeloma. Okay. So it is a particular type of immunoglobulin which is high in blood. Anyway, this is not a class to discuss multiple myeloma. Just remember for now that viscosity can increase due to high hematocrit and high protein content. Fibrinogen, globulin, if these proteins are increased in your blood, then there will be high viscosity. Okay. Okay, next. Next, the formula which you need to know is the Fick's principle. Fick's principle. What is Fick's principle, and what is the use of Fick's principle? So Fick's principle is used to calculate cardiac output. Just we said that cardiac output is 5 liter per minute, or if we convert it into ml per second, it is 83 ml per second. So how to calculate cardiac output? Actually, how to calculate cardiac output? Cardiac output is calculated by Fick's principle, and the formula is oxygen consumption per minute divided by arteriovenous difference of oxygen. So cardiac output is equal to oxygen consumption per minute divided by arteriovenous difference of oxygen content, right? Arteriovenous difference of O2 content. Okay, just simply calculate whether it is coming to 5 liter per minute or not. Okay, if someone is sitting, just relaxing, doing nothing, okay, simply relaxing, how much oxygen you are eating, how much oxygen you are consuming, what is your rate of oxygen consumption? Simply you are sitting, doing nothing. How much oxygen you are consuming? 250 ml per minute. Okay, 250 ml per minute is your resting oxygen consumption. 250 ml per minute is your resting oxygen consumption. So it is 250. Now, content of oxygen in arterial blood and in venous blood. What is the content of oxygen in your arterial blood and venous blood? Roughly, yes, 19 point something. Roughly it is in arterial blood it is 20, and it is in venous blood it is 15 ml per 100 ml. Per 100 ml, right? Okay. So in arterial blood, that is CaO2, matlab content of oxygen in arterial blood, divide minus CvO2, content of oxygen in venous blood, right? So this value is 250 divided by content of oxygen in arterial blood is 20 ml per 100 ml, and here it is 15 ml per 100 ml, and it will come to okay. So this is your cardiac output, 5000 ml, that is 5 liter per minute. Clear? So what is Fick's principle? By Fick's principle, we can calculate cardiac output, and the formula is oxygen consumption per minute divided by arterial oxygen content minus venous oxygen content. Okay, remember this formula, you will have questions from this formula, simply by applying this formula. Okay. Now again, another formula and a clinical setting. And this formula is called the Bernoulli's principle. Bernoulli's principle. What is that? Yes. When blood is flowing in your blood vessel, it has got an energy, right? When blood is flowing in your blood vessel, it has got an energy, and that energy is always constant. Okay? That energy is always constant. and that energy is lateral energy plus half rho v square. Okay, we are neglecting the static energy because it is same everywhere. Okay, we are neglecting the static energy. So the changes are in lateral energy and half rho v square, and this lateral energy is actually the pressure. We can convert the unit of pressure to energy, right? So this lateral energy is actually the blood pressure what we measure. Okay, with this sphygmomanometer, what we measure is actually the lateral energy. Okay. Okay, now what happens? The clinical setting that will be given to you is a patient of atherosclerosis. A patient of atherosclerosis. What is atherosclerosis? Okay, it is dealt in pathology. Yes, actually it is characterized by narrowing of blood vessels, and this narrowing of blood vessel is not due to this vasoconstriction, sympathetic vasoconstriction. It is due to formation of foam cells, which is